Today's seminar will be presented by John Wilson. The subject is on the spin of these satellites. John did his undergraduate work at MIT, came here to Stanford, got his master's degree, and then went to work at Martin Marietta for a few years. Decided that more school was in order, and to prepare for that, he got on his bicycle and went from Oregon to the Chesapeake Bay, was it? And that got him prepared for more circular motion here that he'll tell you about. Clip that to your tie. Okay. Put that in your pocket or clip it.
All right, as long as I'm well tethered. If we could have the lights in front down. Thank you. Topic of my talk this afternoon is the control of a tethered artificial gravity spacecraft. I'll be referring to a spacecraft that consists of a habitat module connected to a counterweight with a long cable or tether. My outline this afternoon consists of 5 sections of the talk. First of all, I'll motivate the research, talk about the physiological problems of long-duration spaceflight, some concepts for an artificial gravity spacecraft, as well as prior related work. Section after that will be a discussion of the modeling that I've done in support of the analysis of the spacecraft. There will be a discussion of experimental results having to do with the operation of this hardware that you've seen up front, some computer simulation results, and then conclusions and recommendations. This outline chart here is actually an error. I will show the videotape between the discussion of the experimental work and simulation work. There are a number of physiological problems associated with manned spaceflight. They are divided into short-duration problems that I won't discuss today and long-duration problems. The short-duration problems include motion sickness, the sorts of things that people encounter on space shuttle flights. The long-duration problems of exposure to weightlessness include decalcification of the bones, skeletal muscle atrophy, and cardiovascular deconditioning. These 3 are not completely reversible upon a return to a 1G environment. An inability to maintain balance in 1G upon a return to Earth or the surface of another planet is also a serious problem. These problems are seen after a stay in weightlessness of 3 months or more, and they would pose a serious threat to any kind of a mission such as a mission to Mars, where there wouldn't be a ground crew waiting to receive the astronauts when they landed. Particularly in the spaceflight programs of the Soviet Union, there have been missions that show the effects of these deteriorations of the human body, and a number of countermeasures have been attempted, including an intensive exercise regimen consisting of more than 4 hours a day of exercise, plus the use of special devices and a number of drugs. But the Soviets have found that the best they can do is slow the deconditioning. They can't stop it. And after a year in space, they are able to see deconditioning about what you would see after 5 months in weightlessness. So no countermeasures have been found, and these problems would pose a threat to a long-duration mission, like a mission to Mars that could take 5 months to go there and 5 months to come back. Artificial gravity has been proposed as a means of eliminating the problems of weightlessness by eliminating the weightlessness itself. The concept of tying the habitat module that the people are in to a counterweight by means of a long tether was mentioned as early as 1925 by Hermann Oberth in his work Ways to Spaceflight. A more recent concept and much more ambitious is the space torus that was proposed in the early 70s by Gerard O'Neill of Princeton University. This concept includes room enough for up to 100,000 people to live in a space colony, and the rotation of the spacecraft produces artificial gravity along the rim. This is a lot more ambitious than what the United States or the Soviet Union can hope to put up in the near future. So what we're thinking about is tying a habitat module to a counterweight with some kind of connective structure, either a truss or a tether. And I will talk about the trade-off between these two alternative structures in a moment. There's some uncertainty about the fastest rotation rate that would be comfortable for the inhabitants of an artificial gravity spacecraft. But it's generally agreed that 2 RPM or less is slow enough that motion sickness is not induced in the occupants. There is the possibility of adaptation to higher rotation rates after a considerable length of time. But going with a conservative value of 2 RPM, this chart of the G level versus rotation rate for different spacecraft radius arms shows that 1 G at 2 RPM would require a radius of 224 meters. So the diameter of the spacecraft would be considerably longer than that, particularly if the counterweight is much smaller than the HAB module. The overall length that we're talking about could be as much as 1 kilometer, and that's much longer than anything that has been built in space so far. Next, I'd like to discuss the alternatives for connecting the habitat module to the counterweight. In steady state, the only structural stress that needs to be carried by the structure is an extensional stress to provide the restoring forces on the two modules to keep them moving in a circle. The truss has the advantage of having a high bending stiffness so that during the spin-up maneuver, oscillations of the structure would be small. However, it has the disadvantage that it's quite massive, typically more than twice as massive as a simple cable or tether, and a large proportion of the total spacecraft mass. It's also very complicated to deploy and could entail a large amount of extravehicular activity should any kind of repairs be necessary. By contrast, the tether can be deployed easily, and the diameter of the spacecraft can be easily varied so that tests can be carried out at different rotation rate and radius combinations. In addition, it's easily storable, and of course it's a lot lighter. So the rest of my talk will focus on the particular issues involved in a tethered artificial gravity spacecraft. And here I'd like to talk about some terms that I'll be using. First of all, the habitat module, or one of the end modules, is the place where the people would live. The counterweight is a mass that has a mass that's probably different from the habitat module. There's really no need to put up 2 habitat modules. It's perfectly acceptable to have one in which people would live, and then a counterweight to provide a restoring force on the tether. And then the tether itself. Most likely this would consist of some high strength to weight material like Kevlar or carbon fiber or S-glass. This is the configuration center of mass, which would generally be closer to the habitat module since it is more massive than the counterweight. And I will be talking about the overall configuration rotation rate or spin rate, omega, and the spin axis, a line that passes through the center of mass. I'd like to briefly discuss some prior related work. There was a lot of work done in the mid to late 60s on the concept of a tethered artificial gravity spacecraft. Most of the work included an analysis of either the tether mass effects on the dynamics of the spacecraft or the effects of rigid bodies. There was only one author who included both of these effects on the dynamics of the spacecraft, and he was able, after making some very restrictive assumptions, to come up with equations of motion for the steady state motion of the spacecraft. However, no analytical studies have included the effects that I found to be important, which include the rigid end bodies, the mass of the tether, the three-dimensional nature of the problem, the orbital effects which actually are of minor importance, and the transient effects involved in the spin-up of the overall spacecraft to the desired rotation rate. Experimental work has been limited to 3 experiments, the most interesting of which was the Gemini 11 mission in 1966. In this mission, the manned spacecraft was tied to a counterweight with a 100-foot-long Dacron tether, and the overall configuration was rotated at a very low rate on the order of a degree per second. The fact that the tether was so short compared to the lengths that we're talking about now means that the tether dynamics weren't that important. We'll see later in my talk that the mass of the tether does have an important effect on the dynamic motions of the end modules after a spin-up maneuver takes place. The contributions of the research that I've carried out include the following. First of all, the experimental demonstration of stable spin-up of a tethered centrifuge with and without end-body attitude control. Secondly, identification of the transient dynamics of a tethered artificial gravity spacecraft during the spin-up maneuver and immediately following, including the important effects of the rigid end bodies, the massive tether, and also different times taken to spin up to the desired angular rotation rate. Thirdly, the development and demonstration of an effective control methodology for spin-up of such a spacecraft with non-negligible tether mass. And lastly, the development and experimental demonstration of a control method for deploying the tether during the spin-up maneuver. The next section of my talk will be a discussion of the modeling that I did in support of the dynamic analysis of the spacecraft. First of all, I'll talk about a complex model or a complete model of the spacecraft. Next, I'll make some simplifying assumptions that lead to physical insight into the motions that take place. And lastly, I'll discuss detail of one of the primary motions, that is the module pitch motions that occur after spin-up. An exact physical model consisting of two rigid end bodies connected with a massive flexible tether is very difficult to do much with analytically. The full equations for this system, these two end bodies connected by the massive flexible tether, are very complex, coupled, and nonlinear, and they're not amenable to a closed form solution. So a common technique that is employed is to model the tether, the continuous tether, as a series of masses connected with springs and dampers. I've chosen for the purpose of computer analysis that I'll discuss later to use point masses, and I can include an arbitrary number of these point masses in my tether model. This finite element model is very useful for computer simulation, but it doesn't lead to a lot of physical insight into the motions that occur. So next I would like to talk about some approximate modes of motion of the system. And the major motions occurring can be divided into three classes. The first being the rigid body modes of the end bodies, including pitch motion depicted here. The second being the spring mass mode, in which the tether acts as a longitudinal spring and the modules move away and toward one another. And lastly, the lateral tether modes, in which the tether vibrates back and forth much like a guitar string under the tension from the end modules rotating. It's interesting to note that the rigid body modes and the lateral tether modes have frequencies that are directly proportional to the overall spin rate omega, but the spring mass mode is independent of the spin rate. Next, I'd like to talk in detail about the pitch motion of the modules, because this is very important to the spin-up of the configuration. The pitch motions are also of great importance to someone who might be living inside one of these modules, because this determines to a great extent what the ride quality in the module would be. This is a picture of a module at the end of a tether that's under tension, and the fact that the tether has tension leads to a restoring torque about the module center of mass whenever there's a non-zero angle theta between this reference line and the line of the tether. The restoring torque, or the tether tension rather, is approximately equal to the module mass times the centripetal acceleration of the module, given by r omega squared, where omega is the overall configuration spin rate. This restoring torque leads to the classical equation for a harmonic oscillator, and the resultant frequency is dependent upon the overall spin rate, omega. These pitch motion oscillations will be seen whenever the configuration spins up, because there's a lot of in-plane excitation when thrusters fire on the end modules. I'll talk in more detail about that in just a moment. The next section of the presentation will be a discussion of the experiments that we've done. First of all, I'll present the experimental goals, talk a little bit about the hardware that we built, also talk about the design of the feedback control system used to quiet the module attitude motions, give the results of a spin-up experiment, and the results of an experiment to investigate deployment of the tether during the spin-up. First of all, the objectives of the experiment were to demonstrate spin-up of a two-module configuration with a tether of negligible mass with and without active in-body attitude control. Next, to demonstrate deployment of the tether during spin-up. Also to provide an experimental validation of the computer simulation that I wrote so that the study that we've done can be extended to a large spacecraft with a non-negligible tether mass. And finally, to provide a test bed for future development of control strategies for such a spacecraft. You see the hardware here on the table, and here's a photograph of the two modules sitting on the large granite table in the basement of Durand. This is the tether that connects them. Each module has an onboard computer for data collection and control calculations. Each module also has two translational thrusters that will fire in opposite directions at the beginning of the spin-up period for about 2 seconds to get the overall rotation rate up to about 5.5 RPM. There are also small rotational gas jets to provide feedback control, as well as a number of sensors that the computer takes readings from, and the results of those readings as a function of time will be depicted on plots that I'll show in just a moment. Some limitations of the experiment include the fact that the tether in this experiment is of negligible mass. However, we'll be able to look at the effects of a non-negligible tether mass on a full-size spacecraft using the computer simulation that I've written. The other limitation is that this experiment is obviously two-dimensional, whereas the motions of a full-size spacecraft on orbit would be three-dimensional. However, the in-plane motions of the spacecraft are decoupled from the out-of-plane motions, and generally the spin-up maneuver will excite the in-plane motions much more than the out-of-plane motions, which are stable and will remain small. So the two-dimensional limitation is a good one, or rather a reasonable one, for studying the spin-up maneuver. Next, I'd like to show how the major motions that I'll be describing in the experimental results are excited by a spin-up maneuver. Initially, the modules will be at the ends of the tether and will be aligned nominally with the tether direction. At some later time, thrusters fire on the end modules in opposite directions, leading to the fact that the modules move in opposite directions. And this leads, since the modules tend to retain their initial orientation, to some non-zero offset angle between a reference line on the modules and the line of the tether. The result of all this is that the modules now will oscillate about their neutral position at the ends of the tether, and that's the pitch oscillation motion that I described earlier. That's what we're going to have to try to control with feedback attitude control jets. The modules behave as rotational pendulums, and so their normal path through this phase plane plot would be a circle if no outside torques are exerted on the modules. However, we want to reduce the amplitude of these oscillations, which here is represented by the radius of this circle. So we use a simple phase plane control logic and size the rotational pulse widths so that it's guaranteed that the size of this circle will always decrease. The quantity that we will try to regulate to zero is the module tether angle, shown here as the angle between a reference line on the modules and the direction of the tether itself. Next, I'd like to show the results of our constant length spin-up experiment. Here the thrusters fired for a period of about 2 seconds at the very beginning of the time history shown here. And you can see the large angle oscillations that take place, greater than plus and minus 10 degrees. This would lead to a pretty uncomfortable ride for anyone who happened to be in one of those modules. There's also some trade-off of kinetic energy, as you can see here, beating between the two modules that occurs because the natural oscillation frequencies of the modules are not exactly matched. This happens to be very sensitive to initial conditions, as it turns out. Now I'd like to show you what happens when we turn the feedback controller on to try to control these module oscillations to zero. And the blue trace there shows the performance improvement that we're able to get. The damping that you see in the natural oscillations is due to the bearing drag of the air-bearing vehicles on the table. This wouldn't be present on orbit at all. The damping would be very low, and these oscillations would go on and on for weeks and weeks at a time. It'd be quite a carnival ride, and there wouldn't be any way to stop and get off. So the feedback controller is effective, and it would be very important for a spin-up maneuver. The cost of the control, in this case, can be expressed as the ratio of the propellant used for feedback control to the total spin-up propellant. In the uncontrolled case, that's 0. In the controlled case that I just showed you, it was 12%. The payoff is that the RMS module tether angle, the quantity we were trying to control to 0, drops from about 5.6 degrees to about 0.2 degrees immediately after the spin-up. And of importance to someone who would be in one of these modules, the lateral accelerations experienced in the module divided by the nominal artificial gravity level here was about 11.5% root mean square, whereas in the controlled case it dropped to about 0.5%. This is sort of like what one would feel in a yacht tossing on a high sea and would make a person sick very quickly, whereas this is sort of like riding in your Cadillac down the freeway, barely perceptible lateral acceleration. Next, I'll discuss the second major experiment that I've carried out. In orbit about a planet, the general method of deploying a tether is to rely on the gravity gradient force, which tends to pull on two modules separated along the radial direction with different forces. So the gravity gradient difference can allow an initial separation of the modules to take place before the spin-up maneuver begins. However, in transit to Mars, the gravity gradient would be very small, and it could not be relied on as a means of separating the modules initially. So one thing that we thought of doing was to deploy the tether while the configuration is spinning. And that's what we've done in the experiment, the results of which I will show you next. The control method that I used was to fire the spin-up thrusters in such a way that the artificial gravity environment in these modules remained constant during the spin-up maneuver. The tether was deployed at a constant rate, and as I said, the spin-up thrusters were fired to maintain a constant artificial gravity level. This is the desired level here. Initially, we spin up to a rate that actually gets us above that, and then as the tether starts to deploy, the artificial gravity drops. The linear accelerometer readings tell the computer that it has dropped below the desired level, and spin-up thrusters are fired to keep the configuration rotating quickly enough that the desired level is maintained pretty well. You can see a spike in the artificial gravity here when the deployment ends and the tether fixes at a constant length. I'd like to show the videotape now, and this will give you an idea of the motions that take place during the experiment. This is a view of the overall lab setup. The computer on the left is used to take data, download data from these two modules that are connected by a tether, and they float on the granite table. The gantry overhead is just to keep the modules in place before the experiment stops. This gives you an idea of the relative sizes of the modules. The pencil in front there shows the size. Each module has a high-pressure gas tank that holds compressed air for the bearing and for the thrusters. Each module also has these two translational thrusters as well as 4 rotational thrusters. The rotational thrusters are used for the feedback attitude control that I described earlier. That's a view of the control and data acquisition computer, and the signal conditioning electronics that are built are on the front there. The computer there runs off of a 9-volt battery. It's a low-power computer originally designed for data logging applications. This is one of the main sensors that I use, and the output of this was recorded on the plots that I showed. That's measures the angle between a reference line on the module and the tether direction. It's a thin film plastic potentiometer. That's a tether reel that allows the diameter of the tether to be varied, and that was used during the spin-up experiment to see if we could deploy the tether while the configuration is spinning. Oops. That's a rotational rate gyro there, originally designed for helicopters, and these are linear accelerometers that measure acceleration in 2 directions. One of those accelerometers, the top one, measures the artificial gravity environment. The ultrasonic ranging sensor there is an auxiliary sensor used to find the distance from one module to the boundary, so we can fire some small correction pulses to keep the experiment from wandering off the table. Here I'll start the experiment. The gantry rises up out of the way. Now the spin-up thrusters fire for 2 seconds. Now the experiment is just gliding at a constant angular rate, or nearly so. It would be so if it weren't for the drag of the table on the modules. You'll see some oscillation between the end modules and the tether in that case because end-body attitude control was turned off. Here I'm downloading data, and this is a plot similar to one I showed earlier of the module tether angle versus time for the two modules. There's more damping in this case than the case I showed earlier because the bearing flow rate was lower in the case recorded here on film, so the friction was higher. This is a case with end-body attitude control turned on and with prior tether tension, and the modules spin up for 2 seconds and then glide. If you were in the room, you would hear a lot of gas jets firing, and that shows the effect of turning the module attitude control on. It quiets those oscillations down rather quickly. Here the RMS oscillations would have been about half a degree or so. Now here's the tether deployment during spin-up, and there's a feedback of the accelerometer reading to the spin-up thrusters to keep the configuration rotating at a rate such that the G level remains nearly constant. The modules start out close together, and there's an initial pulse given to spin the configuration up. Now the tether starts to deploy at a constant rate, and you might see some speeding up and slowing down. There was very coarse control being used in this experiment so that you could see the effect. As the tether tension drops off, as reflected in the accelerometer measurement, a correction is made. Large pulse is given to speed the configuration up again. And this shows a plot of the results. On the upper right-hand plot, you see the sawtooth, which is the artificial gravity environment. That would be a lot smoother if a constant thrust were used during the tether deployment, or a finer control algorithm with a smaller pulse width. These are results from a computer simulation that I will describe next in my talk. The blue lines that you may be able to make out there at right angles to the tether are lines that are fixed in the body axes of the end modules, and the red coming on indicates a thruster firing in opposite directions on the two modules. In this case, attitude control is off and the mass of the tether is rather high, so you can see some large angle deviations between the reference line on the modules and the line of the tether. This is the pitch motion that I've been talking about all along, and it's the major problem encountered during a spin-up maneuver. All right. We could have the lights on again and turn the videotape off. The next thing that I'd like to talk about is the extension of the results that you've seen from the experiment to a full-size spacecraft with a non-negligible tether mass. First, I'll talk about the simulation model used. Next, the spacecraft attitude controller design. I'll talk some about the effects of a non-negligible tether mass. Also the effect of the time taken to spin up to the desired steady-state rotation rate. And lastly, I'll summarize the controller performance. The simulation model used for the physical spacecraft, as I mentioned before, consists of two rigid end bodies connected with a tether modeled as a series of point masses that are connected by springs and dampers. The number of point masses that I use is arbitrary in the simulation, but after comparing the effects of changing the number of point masses, I settled on using 7. It seemed like 4 or 5 gave me more than enough frequency content for the frequencies I was interested in, and 7 was a conservative value to pick. The simulation as written is 3-dimensional, and it also includes the effects of gravity gradient, although these turn out to be of very minor importance for the spin-up maneuver. And as you saw, the 3D graphics output is possible, and there's also analytical output that I will be showing in just a moment. The base case that I will describe that we've done simulations of is an unsymmetric case in which the HAB module is much less massive than the counterweight, about 3 times, or I'm sorry, I said that backwards. The counterweight is much less massive than the HAB module. The HAB module is about 3 times the mass of the counterweight. The overall length is such that there can be a 1G environment produced in the module at 2 RPM. That leads to a radius of 224 meters from the configuration center of mass. This is drawn to scale, so you can see the relationship of the size of a typical space station HAB module to the overall length of the tether, which would be 896 meters, or about half the length of the Golden Gate Bridge. I will show results for 3 different cases. The first case is the case of a massless tether. Next is a tether that has some mass and it has a cross-sectional area of 1 square centimeter. That leads to a safety factor for the tether structure withstanding the forces exerted on it of 1.8, and a tether mass, assuming Kevlar is used, of 125 kilograms. The last case that I'll show to demonstrate the effects of a very large tether mass is a case where the safety factor is cranked up to about 12.6. The tether cross-sectional area is 7 square centimeters, and the overall tether mass is 878 kilograms, which is a little bit larger compared to the total spacecraft mass of a little over 27,000 kilograms. The spacecraft attitude control design is much like that used in the experiment, with one exception. Instead of using the module tether angle that has been depicted as theta on the previous plots, since the tether has some mass, it's going to be going through lateral oscillations. And the quantity of real interest to be regulated is the pitch angle of the module. If the pitch angle is regulated to 0, then the ride inside the module will be good. So what I do is measure the pitch angle beta instead of the module tether angle theta and try to regulate this pitch angle to 0. Meanwhile, the tether can be going through all sorts of lateral oscillations. I'll show here a check that I did to compare the simulation results of what would have been predicted for the experimental results that we just saw. Here are experimental results of an uncontrolled case with the parameters of this experiment and a controlled case. And I'll just show how well the simulation does in predicting this motion with this overlay, and you can judge for yourself whether that's a good fit. This gave me some confidence that the simulation was written correctly. I also made a check against an independently generated simulation that I used AutoLev to generate. And the results for the state vector derivatives agreed to 13 significant digits. So that gave me confidence that at least there were no glaring errors in the programming. I'll show results for a 19-second spin-up to the nominal angular rotation rate of 2 RPM. Here first is a case with a massless tether, and you can see that the oscillations are well controlled to less than half a degree RMS, and the controller torque necessary to do that is very small. Just a few pulses at the very beginning of the spin-up are enough to keep the module oscillations small. Now when we add the effects of a massive tether, the first massive case that I showed with a safety factor of 1.8, you can see that the oscillations are a little bit larger, reflecting the disturbance, the torque that the oscillating tether is putting on the modules. And a little bit greater controller torque is required to keep these oscillations in control. But again, the controller effort ceases even before the spin-up ends at 19 seconds. In contrast, here's a case where the tether mass is quite large. And in this case, the controller has a pretty hard time just keeping the module angles less than plus and minus 10 degrees. You can see that the controller effort continues indefinitely, at least in this plot, and in fact would continue for many months or until propellant ran out, one of the two, because the tether damping is very small and lateral oscillations would not be damped out very fast by material damping. This is clearly an unacceptable use of control effort, and the ride would also be quite uncomfortable. If the controller were off in this case, the pitch motions of the end modules could grow to as great as plus and minus 50 degrees. This led me to think that there might be some effect that could be important on the tether lateral oscillations of the time that it takes to spin up to the desired rotation rate. And this is a plot that is a summary of the results of several simulations using different times to spin up to 2 RPM. This was the case that I just described of a 19-second spin up, and the RMS disturbance torque exerted on the modules by the tether is rather large, over 25,000 Newton meters. However, if we go out even to a half an hour, that drops to less than 40% of its initial value, and a half hour is not a very long time to take to spin up to 2 RPM when one is going to operate at that rotation rate for several months. So the next case that I looked at was identical to the case I just presented, but I used a longer spin-up time. That is, smaller thrusters, and they have to be on for a longer time. And this is the result of that long spin-up with a very massive tether. Here, there is a control effort required to keep the module oscillations under control for the first 3/4 of the spin-up period. The spin-up ends where this tick mark is at about a half an hour, 31 minutes, and the oscillations are fairly well controlled to at least less than 1.5 degrees. So this shows that by changing the module spin-up time, the time to spin up to the desired rotation rate, one can reduce the disturbance environment that the modules are subjected to, and therefore the control effort required. So there's a trade-off actually between the safety factor of the tether and the amount of time that it will take to spin the overall configuration up. In summary of the last case that I just showed you, I didn't show the uncontrolled case, but in that case the RMS tether angle was about 8 degrees. That is the angle between the modules and the tethers, modules and the tether. And the RMS lateral accelerations that I described earlier, divided by the nominal g-force, was about 12%. Turning on the controller cost considerable amount of propellant, 18% of the total spin-up propellant. However, the RMS tether angle dropped to 0.8 degrees, and the important lateral acceleration dropped to 1.1% of the nominal artificial gravity environment. This isn't exactly like a Cadillac on a freeway, but maybe it's like a Chevy. This is clearly unacceptable. That's sort of like riding a carnival ride. Lastly, I'll draw some conclusions and summarize the contributions that I've made. The contributions of this research are, first of all, the identification of the transient dynamics of a tethered artificial gravity spacecraft through experimentation and computer simulation. Secondly, the demonstration through experiment of a stable spin-up of a tethered artificial gravity spacecraft with and without the use of module attitude control. Thirdly, the development and experimental demonstration of a method for tethered deployment during the spin-up maneuver. Also, the elucidation of the effects of tether mass and spin-up time on the behavior of a full-size tethered artificial gravity spacecraft. And lastly, the development of a control methodology for the spin-up of such a spacecraft that allows the module attitudes to be well controlled, and the demonstration of that methodology's effectiveness through computer simulation. There are a number of additional pieces of work that could be done in support of this type of a tethered artificial gravity spacecraft. I'd like to recommend a few. First of all, variable tether length operations can be used to save propellant. If the spacecraft is spun up at a larger than nominal tether length, then the efficiency of the propellant usage increases because the amount of angular momentum one gets for a certain mass of propellant is directly proportional to the module, or to the diameter between the two modules. So spinning up the configuration followed by a reel-in of the tether so that the modules move closer together is something that should be looked at more closely. The fine steady-state attitude control of the modules is an important area of research that needs to be looked into, and I would recommend, of course, the use of reaction wheels or control moment gyros rather than thrusters for the fine control. The use of a movable tether attachment point has been shown by Bob Kleinschoter to enable sub-arc-second pointing accuracies on a gravity gradient stabilized observation platform. And this same technology could be used for the steady-state control of the attitudes of the modules, as well as possibly the spin-up non-steady control. The use of damping devices to augment the damping of the tether so that the disturbance torque exerted on the modules drops faster is an important area that should be looked at. Eric Stoneking is working on this research right now using my computer simulation. And the control of the spin axis orientation of the centrifuge is something that I didn't mention, but that's something of some importance, an issue of some importance, and could be accomplished through the use of gravity gradient torques on the spacecraft. I'd like to acknowledge the contributions of a number of people to this research. First of all, I'd like to thank the NASA Office of Exploration and General Motors for funding the research. I'd like to thank my advisor, Professor Powell, for being a fine man to work for. Carol Kowalski put the experiment together along with myself and was in charge of the air bearing design and all the high pressure fittings, and she did a marvelous job, and I'd like to thank her. Bob Kleinschroeder was the senior member of the Tethered group when I joined, and he offered a lot of helpful advice when I was just getting started. This young man is an instrumentation engineer in New York who happens to be my brother, and he offered a lot of invaluable advice when I was designing the electronics for the experiment. And I would also like to thank the members of the Aerospace Robotics Lab for allowing me to use their large granite table and for offering lots of good advice. And the Laser Diagnostics Lab, including Jim Hellman, who allowed me to use their graphics computer to produce the results that you saw earlier in the film. I'd also like to thank my family for their enduring support and my other special friends, many of whom are here in the audience, and you've made life a joy here. So thank you very much, and I'd be willing to take questions. Yes, sir.
Two questions, John. The first question, how major is the technical challenge to put the tether attach point through the mass center so that would diminish to a great extent your pitch motion due to the torque that you mentioned? And the other question is, when you have a massive tether, when you have a tether with considerable mass, can you apply axial thrust to try and straighten the tether, and would that help with the damping of the transverse motion?
Yes. The first question, as I understand it, is what would it take to, instead of attach the tether to the shell of the module that people would be living in, attach the tether to the midpoint or the center of mass of the module? And that's a good question. One of the advantages of this whole concept is that it could be achieved through relatively low cost. And so a big consideration is using existing hardware. After the space station is built, it might be desired to use a space station HAB module for the place where the people would be living. It would be difficult, I would say, to poke a hole through that HAB module and then rescue the integrity of the pressure vessel and put a tether attachment point at the center of mass, but it's certainly an interesting idea. The other question involves using longitudinal tension in the tether, perhaps with thruster firings prior to the spin-up, to slow the growth of the lateral oscillations that provide a disturbance to the modules. That is something that I've done in an experiment to avoid a sudden snapping of the tether and provide better control. Of course, it's a costly maneuver because it costs some spin-up propellant. The payoff would be, hopefully, that there would be smaller tether oscillations and less of a disturbance to the modules. And that's a trade-off that I really don't know the parameters for. I don't know what you would gain by doing that exactly. I do know that I have tried that in simulation, and even with fairly substantial thrust on the modules, the lateral tether oscillations are still quite large. Yes?
At the beginning, when you were reviewing the history, one of the considerations or one of the criteria for comparison you mentioned was 2D versus 3D. Your experimental work is essentially 2D as it had to be, and I, by the way, think it's very admirable work. And some of your simulations, I think, were 2D and had to be in order to use them to check the experimental work.
Yes.
I wasn't entirely clear on whether or not you had at any point performed 3D simulations, that is, full equations of motion for the end modules in 3 dimensions and then connected by a tether which would not have to remain in a plane
Right.
And if you did not, well, whether you did or not, I'd like to hear what your views are on the problems that might arise, even if they're just guesses, what your feelings are on the subject of 3D effects that have not yet been analyzed completely.
I've not done extensive studies of the 3D motion, but I have done simulations. The simulation is three-dimensional, and I have done simulations where out-of-plane rigid body motions are excited. I found that generally they do not affect the in-plane motion substantially, and as long as those out-of-plane motions are fairly small. So that's my conclusion.
Do they go away by themselves, or do you have to do additional control to get rid of them?
Additional control would be necessary to quiet the oscillations of the modules out of plane. Yes. Yes, Larry.
In the massive tether simulation case, can you compare the frequency and damping of the higher modes, the mass spring mass mode and the tether twang modes?
Yes. The spring mass mode damps rather quickly as a result of material damping in the tether itself. However, the lateral oscillations of the tether do not. The damping ratio is a nonlinear function of the amplitude. So as the amplitude becomes small, the damping ratio goes to 0. That's a problem that Eric Stoneking has been looking at quite extensively and has come up with some good methods for adding a device between the attachment point on the module and the end of the tether that would enhance the damping. And that's the subject of his research. It's a good question. Yes?
Two questions. The first one is, can you describe for us the configuration associated with the two natural modes of motion that we saw trading off in those diagrams? And the second question is, to what extent could reaction wheels or control moment gyros totally replace the use of gas jets? It's just a question of, would you ever have to use gas jets for what is totally an oscillatory behavior?
We started using gas jets initially because that was what was easy to implement on the experiment. I'll answer that question first. The trade-off, of course, if one is desirous of spinning up quickly, is the trade-off involved in deciding how big of a device, how massive a device would be required to generate the control torques required during the transient period, the spin-up period, versus what size of device would have been required just for the steady-state control. So there's a penalty involved in sizing the reaction wheel or the control moment gyro if one decides that it also has to take care of the fairly large disturbances that occur during the spin-up maneuver. But again, lengthening the time to spin up can mitigate the size of those disturbance torques. So the short answer to your question is, if you're willing to wait long enough to get up to the desired angular rate, then it would be possible to spin up without using any control propellant at all. The other question had to do with the beating, the trade-off of kinetic energy between the two modules. And this occurs just because the module oscillation frequencies are slightly different due to slightly different mass properties of the two modules. I found through simulation that one can use modules with different oscillation frequencies and adjust the initial conditions appropriately so that this beating phenomenon is rather small.
I just didn't know what the configuration was. Can you tell us?
Right. Well, I mean, obviously there will be a time during the motion in which the modules are moving together like this, and then gradually one's out of phase with the other until they're going like this, and 180 degrees out of phase, and then it continues until they're together again, like that.
We were looking at the two modules, though, and then first one was moving, and then the other was moving.
Yes.
That's just the beating of those two natural modes that you mentioned.
Yes, that's correct. So one is oscillating a lot, and then it settles down while the other is oscillating a lot, and then the...
That explains the low frequency beat and the high frequency that.
Yes, that's correct. Mm-hmm. Other questions? Yes.
I wonder if you've thought of other types of feed-forward schemes that would eliminate the size of the magnitude of the transient you see on spin-up.
Absolutely. it's possible to adjust the offset of the spin-up thruster from the center of mass in such a way that the angular acceleration of the module exactly matches the angular acceleration of the overall configuration. That's something that one could never do perfectly, of course. So in a real spacecraft, there would always be some small offset. Another alternative to adjusting the direction or the placement of the main spin-up thruster would be to use a small reaction control jet that fires in the same direction and provides a small torque to accelerate the module in the appropriate sense. The advantage of that is that then the attitude control thrust adds to the spin-up thrust, and there's not as much of a penalty, an inefficiency involved in the spin-up.
And then I guess there's not a lot you can do about the finite mass of the tether in that respect.
Except to settle for a smaller safety factor in the tether strength. There are a number of interesting issues involved with deterioration of the tether material on orbit. Kevlar is a plastic, and atomic oxygen on orbit would deteriorate the tether material. So it might be necessary, if we had a research facility on orbit, to replace the tether every couple of years as its strength declined, much like mountain climbers replace their ropes. So there would be an economic trade-off there between how frequently one wanted to replace the tether and how massive a tether needed to be used. Well, supposedly people will want to come home every once in a while.
Would there be an advantage in some cases of spinning it up while it's docked and then just letting out the tether?
Spinning it up while the modules are close together?
In other words, combining the truss and the tether design. You have a truss that's short and you spin it up while it's docked.
Yes.
And then you just let it out.
Well, as you let it out, it will tend to slow down due to conservation of angular momentum. So it is possible to do that, and it turns out that a constant length tether deployment and constant thruster forces would preserve nominally the constant rotation rate of the overall configuration. So that's a good idea. That's something that might be used. Yes?
One last question, Joe. With the massive tether, I don't know why this massive tether keeps sticking in my head, but do you think there would be any merit to cooperating control if you had two modules that had to be controlled rather than one module and one dead weight? Which do you think any merit would be in cooperating control between the two? Could you get any better damping?
The module lateral oscillations are very difficult to control from the modules. I won't say that they are uncontrollable, because technically it's possible to have some effect on the module or the tether lateral oscillations. But in practice, the influence that the modules have over the tether is very slight. So my initial reaction to that is that the modules are going to have to take care of themselves independently. And there's very little that they can do to control either the tether or the other module. But that's something that merits an additional investigation. Larry?
Doesn't that assume a no-torque in condition modules? You have some kind of passive damping there to be able to control energy out of vibrating modes.
Again, as I said, it's not completely uncontrollable, but it is nearly so. And the characteristic times involved in damping out a tether oscillation with a passive damper, such as the one Eric has been looking at, are days, whereas the phenomena that we are interested in occur on the order of minutes or seconds.
Further questions? Thank you very much.
Thank you.